10 years ago you asked me whether it was possible to create a formal system for all physics, I would have likely said no. And not everything can fit in nice and precise definitions. If you ask me now, I would actually say yes. I do think that it's possible to create a formal system for all physics. So what's changed? Well, first of all, as part of my research, I inadvertently started doing it. I didn't realize it at first, but at the end of the day, that's what I was doing. And so if I'm doing it, it means that it can be done. Do I now think that everything can fit in nice and precise definition? No, physics is too complicated for that. The key is really finding which part can be put in the formal system and which part is better to leave outside of the formal system. It's really finding the line between physics and math, and this is what this video is about. I'm going to tell you what I learned and what I wish somebody told me 10 years ago. And maybe you'll find this interesting, maybe you're gonna want to help me with my research, or maybe it's gonna be useful for your own research, but these are sort of the things that you have to keep in mind when you are going to create a formal system for physics. So first, we should have at least a vague idea of what a formal system is. And a formal system, you can think it in terms of three main pieces. The first piece is the set of primitive notions that are in the formal system. These are the basic objects that are taken as is without any definition in terms of other objects. So, for example, in the system of Euclidean geometry, the points and lines are the primitive notions, and nothing. You're basically saying that these points and lines exist, but you never say what they are specifically. You just say that they exist. Then you're going to need a formal language to be able to express facts about these primitive notions that you have. And this formal language is basically going to be a set of symbols and rules of how to put these symbols together so that you can write sentences in the formal system. So, for example, you're going to be using uppercase letters for the points. You're going to be able to use these symbols for segment. You're going to have some other symbols for predicates. You have other symbols to signify logical conjunction, disjunction, so on. So basically the idea of how you manipulate these symbols and what these symbols, how these symbols work. And so that allows you to write sentences. And then with that, you can write the third component of the formal system, which are the axioms. That is, statements about the primitive objects that are taken to be true. For example, again, in the Euclidean geometry, the fact that given two points, there is a line that joins them, that's one of the axioms. And again, if you're creating a formal system, that axiom that here we are just writing in natural language will be written in terms of the formal elements in a language. And so this is essentially what the formal system is. You have to give these pieces to be able to define one. So if we look at the foundations of mathematics, you do have formal systems for all of mathematics, and the most common is the one based on set theory. So the basic elements are going to be sets, and typically one chooses some type of logic, formal logic system, for example, first order logic. And then you have a set of axioms, for example, the Zermelo-Frankel axioms, and you might add the axiom of choice. And then, once you have this, then mathematicians can go and build everything else on top of this. So really this constitutes the basis of the formal system for all of mathematics. And so the question is, well, suppose that you wanted to do something similar for physics. Can we do it? And if we can do it, how would we do it? How can we take physics that it's very messy, that there are a lot of things about experiments and so on? How and what, in what way can we codify all of this? Okay, but at the end of the day, whatever we're going to do, in a formal system, it's always about those three things. The basic notions, the language, and the basic axiom. So we have to figure out how to do that. So for the formal language, well, this is not an issue. We can simply use first order logic or whatever other logic that we have in mathematical logic. It's gonna be fine. There's not gonna be a problem with that. The issue are the primitive notions and the axiom. And here really because these should be justified by the physics. So the idea is that we should have some kind of physical idea, physical system or physical circumstances that we want to characterize, and then from this we are going to have some physical requirement of things that we want to code in the formal system, and based on this requirement then we find the appropriate formal system, the appropriate primitive notions and axioms that are useful to be able to capture those physical requirements that we need to attach. And one of the issues that we are going to find is that there are a lot of things in physics that have to remain in the informal system. So, for example, the connection to the experiment is forever outside the informal system because the piece of equipment that we have in the lab to do an experiment, that's not in the formal system. The how to construct pieces of machinery, whether some pieces of machinery are equivalent to make some kind of detection of some particular phenomena, it's something that again is not going to live in the formal system. And so the idea is really that we're always going to have some piece of information that remains in the formal system, and then we have to map some parts of it to the math. And so it's useful to have this distinction in your mind to really realize that the physical objects live in the physical world and the physical world is in an informal system. And this was sort of my worry that I had at the beginning. And then we choose the axiom of a primitive notion so that we can make a justification that this particular physical object can be represented mathematically with this set of symbols that have this set of properties. And really, we need to find the axioms and the primitive notions we have to choose them in a way so that we can actually justify them in a decent way. And this is already a point of departure that you might have from the definition of a purely mathematical system, because in math you can just define your axiom, the axiom of choice, and you know that in mathematics there are like 10 different ways to express something that is equivalent to the axiom of choice. And but if you had to specify a particular axiom, there may be ways that are simpler to justify physically, that seems more apparent, and some that are not. So that the choice of primitive notion and axioms is influenced by how well you can actually justify things. And now we said, okay, we started exploring this area. We know that there is this dichotomy, not everything is going to be here. We have some choices to make. And now the fundamental question is, what are the type of things that can be captured by a formal system, and what are the type of things that cannot be captured? What are some of the types of problems that we might have? And so here are two things that I think are the worst offenders in terms of trying to put everything in a nice, neat definition. There are two problems that I call one the web of meaning and one the conceptual cut. The web of meaning is really the problem that in natural language and in physics there are no primitive concepts, and things are always defined in terms of other things. For example, if you go to a dictionary and you ask for the definition of a tree, you can see that here it says a woody perennial plant having a single, usually elongated main stem. And then you say, okay, well, I don't know what a plant is. And if you go and look at a plant, it would say a young tree, vine, and shrub. So you have circular definition. Nothing can act really as a true basic notion in a physical system and in the world anyway. So this is the first thing of how sort of the informal world and the formal world works, is that the informal system is really a web of things that are all interconnected to each other. There isn't a starting point, while in the formal system we must have a starting point. And so you need to unroll this web in a way that makes sense, and sometimes this is absolutely not possible. Another thing is what I call the conceptual cut. And basically the idea is that if one looks closely, all physical concepts are well defined only within a restricted realm of applicability. And therefore you're going to have to make a cut that says, okay, this concept is fine because I'm only using it in this realm of applicability. So for example, the idea of an orange, if I'm going to a grocery store or if I'm discussing fruits and vegetables and so on, it's a very clear thing. But if you think of how an orange develops, you can imagine that there is a flower, it gets pollinated, and there is a continuum between the pollinated flower and the orange. And so where is that we make a cut? Where is that we say, okay, from this instant on, we have an orange, and before we didn't have an orange? And of course, there is no such instant. And so if we were to really describe the evolution of an orange, there isn't really a moment where the orange becomes an orange. And things are more complicated. But again, depending on the context that we are, talking an orange would be completely fine. And so, for example, other question that we have here is that can we really define quantities such as distance, time, temperature with infinite precision? That's not what we can do, but in the model we use real numbers and we pretend that these quantities actually have an infinite precise value, even if that's not attainable. When exactly is an object in thermodynamic equilibrium such that a temperature is well defined? Right? At which moment the things in equilibrium, what exactly these elements are difficult to, or probably impossible to specify, but we have an intuitive sense, okay, right now, yes, it's at equilibrium, yes, the temperature is defined, I can take it, and so on, right? So you always have this kind of issue. Or another thing that we want to talk about in physics is about isolated system. Well, but everything interacts gravitationally with everything else, so nothing is really ever isolated. And so clearly at some point we say, okay, but what happens in Jupiter is for the purpose of a car driving on the surface of the Earth really does not matter, and so we can pretend that the system is not influencing this, right? And so there are all these cuts that we make at some point, and we say, okay, it's good enough. This element I can disregard and so on. And all these things are done in the informal world and in the informal system. And once they're done, the formal system is going to be oblivious that we actually made this cut. And there is no single way of making these cuts, and it will be content specific and so on. And so there are choices there that you have to make that are going to influence the formal system. Okay, so this gives us an even more precise map of how this mapping between the informal physics and the formal math happens. We have to recognize that physical concepts are fuzzy and that mathematical concepts instead they are crispy, but they're crispy because we made that cut. These are idealization. And then physical concepts may have circular definitions, and mathematical objects cannot have circular definitions, so we have to find a way to either unroll this definition or really leave the things out such that we can have we can have a linear system. And so what will happen is that some concept will remain in the informal system because they're either left out because we couldn't formalize it, or because really we're making an approximation. We're saying, okay, we're not going to deal these things because they're going to complicate the model, or because they're useless in these particular circumstances and so on. So this is something that one has to keep in mind when mapping from the informal to the formal system. Okay, so now we have sort of figured out a little bit what are the issues, and now we have to decide what is the primitive informal notion that we should have if we want to create a formal system of all of physics, like the one that we are doing in the Assumptions of Physics project. Well, And this has to be something really very, very general, because we want to be able to use the same concept as a foundation for all physical theory. And so we have this guiding principle that tells us something very general, tells us that science is universal, non-contradictory, and evidence-based, meaning that the universal is the same for everybody. We're all going to agree that there is gravity on Earth that accelerates things with 9.81 meters per second square. It's non-contradictory in the sense that either something is true or is false. Something can't be both true and false. When we make an experiment, there's going to be one result. There's not going to be three results, so we need to be able to know what's going to happen. And then it has to be evidence-based. So the truth is determined experimentally in science. So these are going to be about objects and statements and ideas that we can actually go and test experimentally and then see whether these things are true or false. And so if we look at the first two requirements, we need something that is the same for everybody and is non-contradictory. Well, this suggests logics as fundamental, like mathematics, as we saw before. The system in which you write the statements in mathematics is some version of mathematical logic, and that also gives you rules of how to manipulate sentences and so on. And so kind of we shouldn't be surprising that we are going to need for those for physics, but this part is something that needs to be extended. This is something that we do not have in mathematics, because in mathematics the truth is either determined by a proof or it's not determined at all. And so what this suggests is that we should kind of have an extension of the standard logic system. We should have some kind of logic for experimentally verifiable statements, right? So clearly that's something that we need for all physical theories. And these are the type of things that we want to look for if we want to create a formal system for all of physics. We want to find requirements that all physics theory must satisfy, must be able to give us, and having some type of logic of experimentally verifiable statement that sort of brings in this evidence-based feature inside the logic, well, that's something that we really need for all of physics, because all of physics have to be evidence-based. Okay, so what is this notion of verifiable statement? Let's again work in the informal system first. Let's try to understand a little bit what these pieces are. So for example, if I have a statement like chocolate tastes good, this is not universal, because there are some people, poor them, that don't like chocolate. If I said another sentence like it is immoral to kill one person to save 10, well, first of all, it's not universal, because maybe people disagree on this, and it's clearly not evidence-based. We cannot make an experiment to test whether something is morally superior to the other, right? We might test whether people get outraged by that or say things like that, but we can't really test whether morality is not an experimental science. The fact that the number 4 is prime, also this is not evidence-based. Mathematical facts are not evidence-based. We don't make an experiment to check whether number 4 is prime. We actually look at the definitions and we find that 4 is not a prime number because it doesn't fit the definitions. Then we could have things like this statement is false, and again this is not contradictory. We can put in a logic system, and there are lots of other things that we have to learn that shouldn't be in a logic system, because otherwise you have problems. But even if we have something like the mass of the photon is exactly 0 or exactly any number, this is not a verifiable statement because of the infinite precision. We're never going to be able to tell that a photon is exactly 0. It's going to be, 10 to the minus 13 electron volts, something like that. Something that has a finite constraint on precision. That's something that we can verify experimentally. In fact, this is the first example that we have here. The mass of the photon is less than 10 minus 13 electron volt. Now, this idea that we have to put all these intervals for our finite precision, this is something that has to be true for all experimental statements that we have on continuous quantities. So this is going to be a verifiable statement. If the height of the mercury column is between 24 and 25 millimeters, then its temperature is between 24 and 25 Celsius. And these type of statements that we can verify build us confidence that we can actually build thermometer, for example. Or if I take 2 plus or minus 0.01 kilogram of sodium-24 and wait 15 plus or minus 0.01 hours, there will be only 1 plus or minus 0.1 kilogram left. So again, there is a radioactive decay, and whenever we test or prepare our sample for radioactive decay, there is always going to be a finite error bar in our preparation. And so the idea here is that a scientific theory needs at least the concept of verifiable statements. We need to be able to say, okay, these are things that we can verify, these are things that we cannot. And therefore, this makes a good primitive. It's a good primitive notion because it's something that we must have. So there you go. Okay, so now that was the sort of the informal notion, and now how do we formalize this notion in the formal system? And again, here the temptation, especially from the mathematician side, would be to try to capture everything in a formal system. So for example, if we have a statement like the electron is a fundamental particle and has negative charge, we would be tempted to convert it to mathematical logic so that the electron E now becomes a constant, and being a fundamental particle becomes a predicate, having negative charge become a predicative, and so we have Fp of E and Nc of E. This would be sort of a mathematical logic way to encode the sum of this area. And the issue is that this is never going to work. And if you don't trust me, you can go ahead and try to do it, and then you realize at some point this is just adds a level of complexity that it's never going to close. Why? Well, first of all, as I said before, there is this web of meaning. What is an electron? What is math? What is a physical object? What is force? Defining all these things in an absolute way is problematic because things are going to have to reference each other. And in the same way, we have the conceptual cut that we saw before. When is an object have enough to be unmovable? If we had something, unmovable objects, how do we group objects into the same system? How do we say that something is one system or two systems or three systems? How do we do that? How do we divide systems and environment? Even that line, it's you're making a cut for a specific reason, for a specific problem. And so it's not generic. And so trying to design a language that is always going to work is going to be problematic. Then the other thing is that we have different prime elements and different definitions in different theories. For example, before we had electron, we had beta particles, which are the product of particular decays or particular processes, and we didn't know that those were electron, like the identification were done later. So depending on the definition of what you have in different contexts, in different moment in time, you are going to say, oh, we have this definition, or we have this definition. And then you also have problems of semantic paradoxes that are lurking around. If you try to make everything formalized, you are going to be able to say things like the smallest positive integer that cannot be described in fewer than 20 words. And so if you had all these things as predicate, you would be able to construct nonsensical sentences or sentences that are paradoxical in physics, and then you need to gargle with them, and things are going to become very awful very quickly. So we shouldn't try to do this because this is not going to work. And so what is the alternative? I mean, we want to have a verifiable statement as primitive notion. Not breaking it up like this is not a good idea. So what should we do? Well, the idea is that the statement itself is going to be the primitive notion of the formal system. So if we had our statement, the mass of the photon is less than 10 to the minus 13 electron volt, it's a very complicated thing. It means very complicated, there are many complicated elements inside the sentence that one would have to really make precise and so on. Well, we say, well, in the formal system, this is just a point. This is just an element. This thing is essentially a label. The formal system does not know about what the mass, the photon, doesn't know anything. It just knows that there is a statement, the statement is there. And so the formal system does not know or care about the syntax or semantics of the statements. In this way, you simply avoid the problem. And then, of course, you say, okay, well, what can we do with this? And here is the key, is that you have to find the things that at the beginning look like you're doing nothing, but then you layer in just a couple of properties of these things and you get a mathematical structure that is very rich, even though you said very, very little. So, okay, statements should be primitive notions in the formal system, but should they be the smallest primitive notion? So, can we guarantee universality, non-contradiction, and the connection to evidence by only looking at one statement by itself, right? Because at the end of the day, that's what we want to guarantee at the beginning. And it turns out that you can't, because the logical consistency is not a property of a single statement, but it's a property of group of statements. So, for example, if you imagine the liar paradox and you say this statement, this sentence is false, you can realize that this is by itself contradictory. But you could have things like the no-no paradox, in which you say the next sentence is false and the previous sentence is true. Each sentence taken by itself looks absolutely fine. And the issue is that there is this circular reference that becomes problematic. There is another paradox in which the references don't really explicitly go backwards, but they only go forward. And this is sort of another nice thing that tells you, look, the consistency is not for each statement, it's on the whole set. And the other issue is also that the logical relationships and the meaning and everything else are well defined only if you have a consistent semantics that spans through all your statements. So, for example, if you say the Pope is the Bishop of Rome and the bishop can only move diagonally, clearly you can't conclude that the Pope can only move diagonally. The issue is that the Pope, the bishop here, refers to different things. Here is a person in the hierarchy of the Catholic Church, and here is a piece in chess. And so all these things also be straightened out in a way that connects statements to statements. So the statement by itself cannot be an isolated element in the formal system. You have to keep this connection between all the other things that were there. And so statements must be grouped, and what we decide to call this grouping is logical context. And the logical context sort of conceptually keep track of this logic and semantic, but again, they do it in the informal system, they don't do it in the formal system. In the formal system, the logical context is just a set, and it has points, and it's something else outside the formal system that sort of has this idea. It's like from the purpose of the formal system, the informal system acts as an oracle that tells that there is a context and there are these elements that are statements, and that the formal system does not know much else. And now, of course, you also need some connection to experimental evidence. Right now, we haven't done anything here. And again, the idea would be that for having the connection to experimental evidence, we need some type of test. So for each statement we should have that is connected to experimental evidence, there should be a test, and the test can succeed in finite time, can fail in finite time, or can be undefined. And so the idea is success should give us the truth of the statement, failure should give us the falsehood of the statement. But if it doesn't terminate, of course, we can't really conclude anything. And here's the thing is that we don't necessarily have a test that always finishes in all cases. So if I have something like there exists extraterrestrial life, right? If I find experimental extraterrestrial life, then I can stop and I can say, okay, I verified the statement, everything is good. But if I don't find extraterrestrial life, then I just keep looking, because absence of evidence is not evidence of absence. We can't conclude that there is no extraterrestrial life just because we haven't found it. So technically, if the statement is false, we are never going to finish. We're always going to look for more proof and never terminate. So the statement is not really falsifiable, and so we don't have a test that terminates in the false condition. If I say that the mass of the photon is exactly zero, well, this is exactly the opposite. If the mass of the photon weren't zero, at some point we would find an error bar that it's small enough to say, okay, we are outside, zero is outside the error bar, and therefore we can conclude that the mass of the photon is not exactly zero, it's a little bit more. But if we keep going and sort of narrowing in zero, we can never stop, because we always have finite precision. We can make that finite precision maybe smaller and smaller and smaller, but we can never get to zero. So the statement is not going to be verifiable, it's going to be falsifiable. Or something like the ratio of the mass, the ratio between the mass of the electron and the mass of the proton is a rational number. Again, this would require knowing everything to infinite precision, and this is never gonna happen, right? We are always going to have a finite approximation for that ratio, and to know whether that ratio is rational or not, we would have to go at infinity and see if this expansion keeps repeating forever. And so, even for things that we care about experimentally, it's not necessarily true that we always have tests that are always going to determine that true and falsehood, in which this is actually what makes the mathematical structure that we need a lot richer than what you would expect just by saying some things. And so the idea of a verifiable statement then is that if the statement is true, we are guaranteed success. We can't have, if the statement is true, the test can't go on forever. It needs to, in finite time, finish and tell us, yes, this statement is true. And so this would actually be the part that we want to capture conceptually in the formal system. And what it turns out, though, is that trying to capture the experimental tests themselves and all this business becomes very, very cumbersome. And again, it's something that, in retrospect, is better not to do. The only thing that turns out that you need to do is to say, okay, I have a context, which is a set of statements, and there is a subset of these statements that are verifiable. And then you can put axiom on this verifiable statement because of the finite precision. They are going to show that these follow a logic that is slightly different than standard logic. But you don't want to put the test in the formal system because they just add complication. They don't really help. And so this is basically what we found, that that works, and you can create a rich structure on it. And I'll have other videos that go into the details of this. And just with these simple objects, you're going to be able to get to topologies and the sigma algebras and these mathematical structures that are the foundations of all other mathematical structure. But again, conceptually, we'll say, well, is this primitive enough? Is the idea of having these statements that are verifiable enough to be able to describe, for example, equations and differential equations, stuff that we typically do in physics? And so to see that that's the case, we can imagine, for example, Newton's second law, F equals ma. And typically we think this FMA as a real number or vector quantities. We're doing in one dimension just to make the task simpler. But really, again, these equations are always in terms of some type of finite precision, because at the end of the day, that's what we do in physics. So you can imagine that if we if we have a force with some kind of finite precision, so we are basically means that we have a statement about the finite precision of the force. We're going to have some value for math, which again means we have some statement on finite precision of the mass, and we are going to have a statement about the finite precision of the acceleration. And so what the equation is really doing is expressing some logical relationship between the statement. It basically says that if the mass is m plus or minus delta m kilograms and the acceleration is a plus or minus delta a meter per second square, then the force is going to be m times a plus or minus some uncertainty on the f that in principle we can calculate, but it's going to be a little bit more complicated. And so the equation is really expressing relationship between experimentally verifiable statements, and this makes sense because if we have a physics equation and we say that physics is evidence-based, it should be that at the end of the day, whatever we are discussing in our physical theory, we can turn into verifiable statement, things that we have tests, and then we can go and execute the test and check that these things actually work. And so the idea is that we can actually construct a formal system for experimental science, provided that we understand that physics will always live in the formal system, so not everything will be in the formal system. In fact, the most important thing, the most important reasoning about physics will happen in the informal system, like, the conceptual cut and stuff like that, will happen in the formal system because it will tell us how to simplify the problem such that we can create the formal system and set of equations and create a model for it. The formal system is made precise by removing all the things that can't be captured in a precise way. So there is this idea that math is like perfect and physics should be like math. But the problem is that math is perfect, can have the level of precision, because not because it captures everything, but because it cuts away the things that are problematic. And you can really see in the foundation of mathematics, like the trick that you have, for example, in set theory and so on, is to find some kind of way to say, okay, these are the statements that we allow, and we allow these because we're not going to get into trouble with logical inconsistency. So it's really by removing all these problems and sort of saying, okay, we're only going to look at this little set of problems that actually things get work. So the precision in the formal system is there because we have removed all the things that are problematic. And this, again, helps you understand what you're doing when you're going from the informal system to the formal system. And then we saw that generally in physics, the logic system needs to be augmented to keep track of experimental verifiability. And this is how we should look for requirements for things that we must have. Now, is this enough? Do we need more things? Well, that's going to be a topic for other videos. And the other thing that one should keep in mind is that primitive notions should be specifically chosen to expose only the necessary complexity. As we saw when we were talking about verifiable statements, the tests are there in the back of our mind, right? They're still part of the informal system, but we don't want to put them in the formal system because they're just going to increase the complexity and they're not going to help the formal system be more expressive. So why should I put them? It's better to keep the formal system simple and make it do the thing that it needs to do more easily. And then the other thing that this is something that we're going to look at other videos when we are going to talk about the way that we specifically do things in assumptional physics. Axioms and definitions should be specifically chosen to have straightforward justification. So the goal here is not to find some clever way to define things that mathematically is beautiful. No, it has to be the simplest thing that we can justify from the physics side. For example, this idea of verifiable statement, that's something that we must have from the physics world, and so it's very readily justifiable, and those are the type of things that we want to have. And when we want to then write axioms about the verifiable statement, what are the things that we can do with verifiable statement, there should be a small justification that it's easy enough to say, okay, you've convinced me that verifiable statement must have this property, must allow for these type of things to happen. So that's basically it for now. These are the type of things that you really need to have in the back of your head when you're writing a formal system for physics. And in the future videos, I will show how we actually develop these concepts in the assumption of physics frameworks, and show how verifiable statements are tightly coupled to topologies in mathematics, and how just the general notion of statements that are related to a test is instead associated to sigma algebras. And if you've never heard of sigma algebra, the sigma algebras are the things on which we construct theories of integration, measure theory, probability theories. All of these things are defined on a sigma algebra, and again, all these things are in the end related to experimental verifiability. So I hope that you found this interesting, and see you next video.